Hi everyone, this is the first of two parts where we're going to have a look at density, pressure and upthrust, and we're going to consider why it is that certain objects float while other objects sink. So a good example would be if I have a piece of metal, a lump of metal, and I throw it into a container of water, I would expect that to sink. However, a submarine, which is made out of an enormous amount of metal, is able to float. And so we'll consider the differences in what's going on there. If you had a lot of time on your hands and you could gather together a whole range of different coloured liquids and solid items, and you pulled them all into a big cylindrical container, eventually they would separate out according to their density, and you could recreate that image that you've got on the left hand side. So let's consider in this video density and pressure. Firstly, density. Now this is something that you've met before. We define density as the mass per unit volume, and from that the equation is density equals mass divided by volume. The symbol for density is the Greek letter rho. And in terms of the units of density, various units can be used. And it's important that the units of density reflect whatever units you're using for mass and for volume. So, for example, density could be measured in grams per centimetre cubed. If that's what you've measured mass and volume in, equally it could be measured in kilograms per metre cubed. And it's just important that you're consistent with your units of density, checking that they reflect the units of mass and volume. In terms of calculating volume, I'm hoping that you're all familiar and confident in working out the volume of cuboids, cylindrical objects and spherical objects, and you've got the reminder of how to do that on that slide that's in front of you. Just a quick note on converting units then, because often we are required to work in kilograms and meters cubed. So let's talk about converting volume. So if we've got something where all of the dimensions are in centimetres, we've got to convert those into meters. It's a reminder that a centimetre is 10 to the minus 2 meters, and a centimetre squared is 10 to the minus 4 meters squared, and centimetres cubed is 10 to the minus 6 meters cubed. So the rectangular object that you've got on the left, you would need to divide each of those dimensions by 100 to convert them from centimetres into metres. In other words, 1 centimetre cubed is 10 to the minus 2 cubed meters cubed. And that's where the 10 to the minus 6 comes from. And similarly, for millimetres, you know that a millimetre is 10 to the minus 3 metres. So a millimetre squared is 10 to the minus 6 metres squared. And a millimetre cubed is 10 to the minus 9 metres squared. So in other words, to go from millimetres to millimetres cubed, it's 10 to the minus 3 cubed meters cubed. And I've just noticed I just need to correct that final expression, so it says meters cubed. Okay, it's worth having a practice then with the 3 examples on that slide to check that you're happy making those conversions. So in terms of using the density equation, let's just have a little look at 2 examples. Firstly, the neutron star. Neutron stars, remember, are incredibly dense. So let's calculate what that density is. The mass is 3 times 10 to the 24 kilograms. And we'll assume the neutron star is spherical. So it's got a volume which is 4/3 pi r cubed. And the radius is 12 kilometers. So that's 10 to the 3 cubed. You mustn't forget to cube the radius, otherwise your answer will be significantly incorrect. And when you calculate that, you get a value of 4.2 times 10 to the 11 kilograms per meter cubed, which is an absolutely phenomenal density. So if you had a 1 by 1 by 1 meter cube, and it was of the same density of a neutron star, it would have a mass of 4.2 times 10 to the 11 kilograms. If we compare that to the density of Earth, and the reason I'm making this comparison is because the mass of the Earth isn't that dissimilar to that of a neutron star. It's only doubled. However, the volume of the Earth is significantly different, and we're about to cube that difference. So the radius is 6,400 kilometers. We're going to cube that, and when we do, we get a value of 5.5 times 10 to the 3 kilograms per meter cubed. So you can see the difference there that radius has on volume and therefore on density. Okay, so the average density of the Earth is about 5,500, and that was a good piece of evidence for the Earth containing iron. Iron has a density of about 7,000, and it was known that the surface, the crust of the Earth at least, had other substances of lower densities, so that helped them kind of piece that together. Okay, let's discuss pressure then. Again, this is something that you've come across before, and those of you who did the separate science, you've done more on pressure than those of you who didn't. But let's start right back from the beginning. We define it as the force per unit area. And from that, we get the equation pressure is force divided by area. And the force acts normally to the surface. That word normal, again, it means at right angles. So in other words, if I take this object here and I submerge it underwater, it's under a greater amount of pressure, and the force acts normally to each surface. Okay. Now, we've got a variety of units that we could use for pressure. The Pascal is one, named after Louis Pascal, who was a bit of a pioneer in the work of us understanding pressure in the atmosphere. But obviously, we can derive units from the equation. Force is measured in newtons, and area is measured in meters squared. So 1 Pascal is equivalent to 1 Newton per meter squared. And you can use either unit. Both are equally valid. In terms of converting into SI units then, let's see if we can get to the SI units that have been presented to us. So pressure is force divided by area. So in terms of newtons, it's newtons divided by meters squared. The Newton obviously is not an SI unit, so I might use Newton's second law in order to get the unit of the Newton in SI units. And we've got, let's turn that off, we've got kilograms, and acceleration is meters per second squared. So if I go back up to here again and make that substitution for newtons, so it's kilogram meters per second squared, and I've already got the 1 over meters squared from before. Okay, can cancel out for one of the meters, and so we're left with kilograms. I've got 1 meter left on the denominator, so I've got meters to the -1, seconds to the -2. That agrees with what we've got on the screen. Okay, so the idea of pressure then is all about force and area and the ratio of those two. So when you stand on the floor, your weight is the force of gravity acting on the floor, and the area is the area of your 2 feet, the surface area of your 2 feet. When you sit on the floor, that involves a larger area of your body, and so therefore the pressure on the floor is going to decrease. If you wore some shoes with small heels, so the kind of stiletto heel example, which has got very tiny surface area, your weight is now being shared over a small area, and therefore the pressure on the floor is going to be much, much greater. So it's all about the interaction of those two. So when we're talking about pressure then, and we've got an example like we've got in front of us here, we have to acknowledge that both force and area contribute to pressure. So the tractor is not sinking into the ground, even though its weight, i.e. the force on the mud, is greater, but it's also about the area of those tyres. The area of the tyres has increased by more. So in other words, if the tractor is twice the weight of that car, the area of the tyres might be 10 times the area of the tyres of the car. And so the pressure on the mud is reduced, and therefore the tractor doesn't sink into the mud. Okay, let's look at it from a slightly different perspective. So what's the best implement to chop a piece of wood? Something with a sharp blade. Why is that? Because I am only able to supply a certain amount of force. Okay, I've got a fixed force that I can swing that axe with. So if I can sharpen that blade so that the area is very small, then the pressure on that wood is very high, and therefore I'm able to split that wood more easily. Okay, so when we're describing the effect of pressure, it's all about that ratio of force and area. So here's a rather bizarre example that we can have a look at then. So a yogi, somebody who practices yoga, can apparently perform this. Never tried it, not sure I'm that tempted. But if we made a board and banged 336 nails into it, we could test out the claim that it takes 690,000 pascals to break the human skin. Okay, let's see if that's correct then. We're told that the radius of a nail is 0.1 of a centimetre. So in other words, each nail, which is what you're going to lie on, the tip of the nail, has an area of pi r squared, but we've got 336 of them. So let's assume that this yogi is laying on every single nail. So in other words, the total amount of area of those nails is 336 lots of the area of one nail. So that's 336 lots of pi times. Radius is 0.1, it's centimetres squared. And if we calculate that, we get 1.06 times 10 to the minus 3 metres squared. You can check that you get the same outcome. So we need to know what the pressure is then acting on them. So that's force over area. So that's the weight of that person. I don't know, typical person, 70 odd kilograms. G is roughly 10, isn't it? So we multiply mass by about 10. So let's say that this person's got a weight of 700 newtons and it's being shared out over this area. And when we calculate that, we get 663,145 pascals. Okay, that is the pressure acting on the skin of our yogi. The question says that skin breaks at 690,000 pascals. So we're a little bit close, but we are under that, aren't we? The pressure on that person's skin is just less than the breaking pressure of skin. But I guess if that person was a little bit heavier, that may not suddenly be true. So there we go. Not a challenge that I recommend you undertaking. Now, when we're talking about pressure, we're going to divide it into two different types of pressure. The first is atmospheric pressure. So I don't know whether you've thought about this before, but there's about 10 kilometres of air above you where you're sitting or standing now. It's almost like there's this invisible column of air above you, extending about 10 kilometres right to the top of the atmosphere, and it represents about 10 to the 4 kilograms mass of air. Gravity is acting on that, so it's kind of acting on you. There is a force on you, giving rise to a pressure on you. And we call that atmospheric pressure because that's where it originates from. Okay, it's got a value. Atmospheric pressure is about 100,000 pascals, 101 kilopascals. But you and I aren't aware of that. And the reason for that is because the pressure acting from the atmosphere on us is equal to the pressure inside us acting outwards. We've got an equal amount of pressure acting in and out from our bodies. So therefore, those two pressures cancel out. and we're not aware of it, but it is there, and we are going to need to take it into account shortly. The other kind of pressure we sometimes refer to as hydrostatic pressure, and it's the pressure associated with a fluid. Now, you could argue, well, the atmosphere is a fluid. Why is that not called hydrostatic pressure? It's no different. It's just that we need to distinguish between it and other types of pressure often. So we've got an example of a balloon. The balloon is under pressure. We have inflated it. We've put our own air from our lungs inside of the balloon, and that is acting normally to the surface. That force from that pressure is acting normally to the surface area of that balloon. But of course, we don't live in a vacuum. There is atmospheric pressure, and that is acting normally to the surface balloon, but from the outside, pointing inwards. So we've got these two pressures. Now, the pressure of the balloon is greater than the pressure of the atmosphere. So therefore, what does that mean? It means that there is a resultant force and it is acting outwards. What does that mean? Because we've got an elastic material, Hooke's law says that it's going to extend, because that elastic balloon will have some kind of spring constant, and so the balloon will stretch, it will inflate. And it's the Young modulus which is going to determine the strength of that balloon, i.e. when is the balloon going to burst, when is it going to pop, okay? So there's a nice little link here between pressure and forces and that work that we've done earlier in the year when we looked at materials. So is it possible then to quantify and calculate the amount of hydrostatic pressure that exists? The answer is obviously yes. So on the left, you've got a little derivation and an equation. So let's consider that we've got a container full of liquid. The depth of that liquid is h meters, and the cross-sectional area of that container is A. So volume of the cylinder is area times height, isn't it? HA. Mass is density times volume. So the mass of the liquid contained in that container is the density multiplied by HA, which was the volume. Okay. Now I want to know what force acts if I'm at the base of that container. So that is the mass of the water multiplied by G. So we get rho HAG. And now we can calculate the pressure. Pressure is force divided by area. So that's rho HAG divided by area. And I can cancel out my areas, tidy that up by just rearranging the letters. And we get rho GH as our way of calculating pressure. Okay, now just be careful about what we mean by H. H is depth. Okay, not height as such. It's the depth below the surface. So this is telling us then that the further down you go in a liquid, the greater the pressure. And you kind of know that. So if you've ever done any diving, the deeper you go, the greater that pressure. You feel the force of the water acting on you. And there's obviously a limit to the depth that you can dive to before that pressure becomes too great. I don't know how you'd achieve this, but if you went somewhere where G was greater, the pressure would be greater as well. And the density of the fluids that you're in also makes a difference. So if you went swimming in a swimming pool full of, I don't know, treacle or something like that, then for a given height, that pressure would be much greater on you. So in other words, there is this direct relationship between pressure and height. They are directly proportional to each other. Did I say height? I meant depth, pressure and depth. Okay. So when we're calculating pressures, often we need to combine both the atmospheric and the hydrostatic pressure. So I won't go through this example with you. You can look at that in your own time. But if we've got a diver 30 meters below the surface of some water, so there they are. Look like they've kind of passed out, don't they? 30 meters below, that's the depth that they're at. We have to recognize that the total pressure being experienced is a combination of the atmospheric pressure and the fluid pressure, the hydrostatic pressure. Okay, in other words, the rho g h pressure. So you would add those two together, and that would give you the total pressure that person was under. Okay. For the last little moment in time then, let's just have a look at a few kind of applications of this. So let's have a look at one of the early ways that the atmospheric pressure was actually measured. And it was measured using what we call a mercury barometer. And what you do is you get a trough and you fill it with mercury, and you invert a cylinder with mercury, making sure that you leave a gap at the top, a vacuum, and that enables the mercury to rise and fall within that glass tube. Now, the atmosphere is able to support a certain height, believe it or not, of mercury, even though mercury is like this really dense liquid metal. If you had it in your hand, which we're not allowed to do anymore, okay, there would be a lot of mass, so there'd be a lot of weight in your hand at that point. And the atmosphere is able to support a certain amount of height, because what we've got is the atmosphere providing a downward pressure on the surface of the mercury in that trough. And that means that when gravity acts on the weight of the mercury in the column, those two forces are able to counteract each other. And so as the pressure of the atmosphere changes, the weight and therefore height of mercury that's able to be supported also changes. So when you're listening to the weather forecast, you may clock phrases like tomorrow it's going to be a high pressure day, or the pressure's going to rise tomorrow. That would mean there would be an increased atmospheric pressure acting on that trough of mercury, and that would be able to sustain a greater height of mercury in the column. So the height of mercury in the column would rise. So this was measured, and the person who did this, their name's completely escaped me. It might come back to me in a few minutes. But they set this up at sea level, and over the course of a period of time, measured the average height of mercury that was supported, and they found that it was 760 millimeters. And from that, a definition of atmospheric pressure was derived. That was referred to as 1 atmosphere of pressure. So if the atmospheric pressure was 1 atmosphere, you were being told that it was able to support 760 millimeters of mercury. Now, what is that in kind of SI units? So let's use our hydrostatic pressure equation. The density of mercury, which you've got on the screen, is 13,546 kilograms per meter cubed. G is 9.81. And on average, we are supporting 760 millimeters of mercury. Okay, when you do that calculation, you get a pressure of 101 kilopascals. Okay, so all of these three units are essentially equivalent to each other. A pressure of 101 kilopascals is equivalent to 1 atmosphere, is equivalent to 760 millimeters of mercury. Okay, it's not often they do this now on the weather forecasts, but sometimes they do give you the actual pressure of the atmosphere for each day. So why do we use mercury? Why do we not use water? Well, we could, but the thing about water is it's about 14 times less dense, 13.6 times less dense. So that means then that we would be able to support a 13.6 times more water in the column, i.e. the column would be 13.6 times taller than the 760 millimeters. That's pretty close to 10 meters. Okay, not very practical. So a mercury barometer is just simply more compact than a water barometer would be. Okay, that's the end of what I need to talk to you then about density and pressure. And I'm very happy if you want to stop at this point. For a couple of minutes, I'm just going to go through just some examples which are kind of like beyond the spec, but just give you that kind of background knowledge. So if you want to keep listening, please do. Or if you want to stop and come back at some point later in time, then I'm equally happy with that. Okay. I noticed when I flew for the first time that when I took some food that I bought on board the plane with me, the crisp packet was like about to burst. It really looked inflated. Now, obviously, it hadn't. It's a sealed crisp packet. And that same crisp packet, when we landed, went back to its kind of normal kind of level of being inflated again. Okay, so the question is, why is that? So when I was at the airport and I bought my bag of crisps, it was about 1 atmosphere of pressure. So that means that the pressure inside my bag of crisps was about 1 atmosphere. The pressure in the airport building was about 1 atmosphere. It was about the same pressure inside and outside that bag of crisps. But as I get into the plane, one of the things that pilots do as you start cruising to higher and higher altitudes is they drop the pressure in the cabin. And so that means that in the plane now, there is less than 1 atmosphere of pressure, but my sealed bag of crisps still has 1 atmosphere of pressure inside it. So now there is greater pressure inside than outside. So in terms of drawing those kind of pressure arrows, okay, I would draw smaller arrows for the pressure outside than inside. So the resultant pressure acts outwards, okay, forcing that bag to look like it's inflating. Okay, so why do pilots do that? It's basically to kind of just give the plane longer life, basically. So when you're cruising at 60,000 feet or whatever, the pressure of the atmosphere is quite low. If you kept the pressure of the cabin at an atmosphere like it was on the runway, there'd be a big difference between pressure inside and pressure outside. And that would be putting big forces on the body of the plane. And over time, forces tend to fatigue metal, and that would reduce the lifespan of the aircraft. So what pilots do as they're increasing altitude is they reduce that atmosphere inside the plane. That's why your ears pop when you're taking off and you're landing. You're sensing that change in pressure. And what they're trying to do there is reduce the difference between the pressure inside and outside of the plane. Okay, a couple of quick fire things. The classic trick question. I've got a 6-litre fire extinguisher under a pressure 10 atmospheres. I open the valve and I let all of the CO2 out. But actually that isn't what happens. There is a certain amount of CO2 that stays in the fire extinguisher. It'd be really odd if all of the CO2 entered into the room, because you'd effectively be left with a vacuum inside the fire extinguisher. So actually only 9 atmospheres of CO2 leave the fire extinguisher, leaving you with 1 atmosphere inside the fire extinguisher, which is the same as the atmospheric pressure in the room. So in other words, when you release a canister that's under pressure, the pressure falls until it reaches the same value as the room that it is in. And at which point there's the same pressure inside and outside of that canister, and so the gas neither moves in nor moves out. So can you then apply pressure to something like a gas, get those particles closer together? Can you turn it into a liquid? Can you keep applying pressure and turn it into a solid? The short answer is no, you can't. And the reason for that is there's too much energy at that temperature for the particles to remain kind of in that orderly lattice that they would need to remain in the solid state. So one of the things that you're doing when you're going from a gas to a liquid to a solid is you're removing kinetic energy out of that substance. That's what lowering the temperature does. So that enables then those particles to come into that more ordered lattice arrangement. And then finally, boiling and evaporation. We'll come on to that in a second. The boiling point of water is determined by atmospheric pressure. And you can watch that little YouTube clip of somebody who takes a canister of water up, I think it's Mount Everest, and the boiling point of the water decreases the higher that he goes. So as the pressure of the atmosphere decreases, the water boils sooner and therefore at a lower temperature. And so you can actually get water boiling at like 80, 85 degrees on the top of a mountain. So that sounds like an advantage. That sounds like it's going to be easier to get that water to boil. But those of you who like a good cup of tea, or maybe let's use a cooking analogy, boiling pasta. Pasta needs the water to actually be at about 100 degrees to become soft. So if you try and boil pasta at 80 degrees, it just won't soften in the same way. So have a little look at that YouTube clip if you're interested in that. And then finally, an idea that we'll pick up on in year 13, it's the difference between evaporation and boiling. They're two very different things, often confused to mean and be thought of as the same way, but you've got a nice little summary of those two.